Hello everyone. Welcome to this week's Math Physics seminar. We are pleased to have Arpan Saha from ICMAT, the Institute for Mathematical Sciences in Madrid. He will give a talk on Gromov, Witten, Donaldson, Thomas correspondence, resurgence, and geometry. Arpan, take it away.
Yeah, thanks, sir. Thank you for the introduction and the invitation to speak at this seminar. So today, I'm going to be talking about some recent work inspired by a research program of Tom Bridgeland, and which brings together the Gromov, Witten, Donaldson, Thomas correspondence, resurgence, and the geometry of supergravity compactifications. Although I am currently based at ICMAT in Madrid, this talk is based on work carried out at Hamburg and Oberwolfach in collaboration with Murad Alim, Jörg Teschner, Iván Tulli, and Mauro Mantegazza. Okay. So let me open with a bit of motivation. So Gromov, Witten, and A-model Donaldson-Thomas invariants both have to do with counting holomorphic curves, that is, holomorphic submanifolds of complex dimension 1 sitting inside a larger space X. Now, this problem by itself turns out to be poorly defined, but we can fix this by introducing a subtle bit of extra structure. And where GW and DT invariants differ is in the extra structure that they introduce. Okay. Now, GW invariants count isomorphism classes of holomorphic curves along with a parametrization by what is generically a Riemann surface, which is to say it counts holomorphic maps from a Riemann surface to X. DT invariants, on the other hand, count isomorphism classes of holomorphic curves along with what is generically a holomorphic line bundle over the curve.
Can I ask a question? Sorry.
Sure, yeah.
That's very early, but when you say A-model Donaldson-Thomas invariants, I would have thought, like what would come to my mind is like you would be counting stable objects in Fukaya categories. And so the DT invariants would be special Lagrangian counting special Lagrangian submanifolds with some decoration.
Right. I'll come to this in the next slide. That's a great question. I'll address this point in the next slide. Okay. All right. So the extra data leads to different behavior under degeneration, and so the GW and DT invariants really do count different things. However, it has been conjectured by Maulik, Nekrasov, Okounkov, Pandharipande, and proven in many classes of examples that the knowledge of all GW invariants is enough to deduce the DT invariants and vice versa. Well, the conjecture is actually a lot more precise than the statement over here, but this is where I'll leave this for now.
Could you kindly please explain what DT invariants are in a bit more detail?
I'll come to it. I'll address that. Okay. So, well, it turns out that GW and DT invariants, they both have physical interpretation. Now, GW invariants are coefficients in the genus by genus perturbative expansion of the A-model topological string-free energy. Meanwhile, DT invariants are degeneracies of non-perturbative bound states in A-model string theory. Now, as was it Pranav who asked the question?
Yeah,
about the A-model.
That's right.
DT invariants. Okay. Anyway, so you might be wondering that aren't holomorphic curves B-model objects? So why are you counting holomorphic curves in A-model topological string theory, right? Well, the answer is that both special Lagrangian submanifolds and holomorphic curves are present in the A model as well as the B model, but they play different and complementary roles. In the A model, special Lagrangian submanifolds, they play the role of boundary states. So they are objects in the categorical sense, right? Whereas holomorphic curves play the role of bound states. In the B model, it's the other way around. So in order to convince yourself of this, note that the Kähler form is something you integrate over a holomorphic curve. So a holomorphic curve is charged with respect to a Kähler form, whereas the holomorphic volume form is something you integrate over a special Lagrangian submanifold. That is to say that a a special Lagrangian submanifold is charged under a holomorphic volume form. Does that answer your question?
Yeah, no, I understand this, but I still don't understand. I mean, so DT invariants are going to count. So a priori, DT invariants are going to count stable objects in the Fukaya category. Is that a true statement or not a true statement?
There are two versions of Donaldson-Thomas theory. There's the A model Donaldson-Thomas theory and the B model Donaldson-Thomas theory. I guess like
I'm talking about the A model one because you're talking about the A model.
Right. So the way I'm going to set up things, basically the more natural thing here will be counting holomorphic curves rather than special Lagrangian submanifolds, basically. Because
is there some sense in which, so let me explain where my question is coming from. If you are in dimension 2, then you can, there is a correspondence between Lagrangians and holomorphic objects because of hyperkähler,
hyperkähler rotation,
yeah, exactly. But in dimension 3 there isn't, so I don't understand like what the correspondence is between what I'm calling A model Donaldson-Thomas invariants, which are counting, in the sense of Kontsevich and Sovelman, where you're counting stable objects in the Fukaya category, and what you're calling A model Donaldson-Thomas invariants. Are they different things?
Yeah, they're different things because
okay, fine. Okay, then it's okay.
Yeah, these are different things. Okay. So maybe you might object to me calling it the A model Donaldson-Thomas theory. And in fact, there was this math overflow question asking about this thing, like if the GW invariants and DT invariants are like both supposed to be encoding the same thing, then then why are the DT invariance countings supposedly B model objects rather than A model objects? And the answer is that, well, it's a bit of a question of interpretation. Like, sure, special Lagrangian submanifolds, they are the boundary states. Like they define the objects of the category underlying this topological string theory, right?
Yeah.
But that's not what I'm talking about. I'm talking about bound states in the sense of instantons.
Okay. So I mean, it's fine. I just wanted to clarify that,
sure. Yeah, right.
Like A model DT meant something to me. So I just wanted to. So you're talking about something different. Yeah. Thanks a lot.
Yeah. And by the way, feel free to interject anytime. So I think it makes for a much more interactive talk, and it's helpful to me actually. So please feel free to ask questions whenever. Okay, so to continue with the story, the general story that we have in physics is that perturbative and non-perturbative sectors of a theory are related by the phenomenon of resurgence. And so we expect that resurgence will be the link between the GW invariants and the DT invariants, okay? And in this talk, we shall see that this is in fact true in the case of a certain example of non-compact Calabi or threefold called the resolved conifold. So this is going to be the plan for the talk. First, I will discuss some preliminaries where I will introduce the ingredients of the correspondence. In particular, as someone asked, I will actually say what DT invariants are. And then I will apply this machinery to the generating series of the machinery of resurgence. I'll also introduce what resurgence is. Then I'll apply the machinery of resurgence to the generating series of the GW invariants, okay? And then I'll tell you how you can read off the DT invariance from that. And finally, I will discuss how all of this can be interpreted in the context of certain geometric constructions coming from supergravity. Okay. So that's the plan, and let's get started. Okay, so let us fix a Calabi or threefold X, and let us also fix a basis of holomorphic curves generating its second homology. Then, given a tuple of non-negative integers d, we may ask how many holomorphic maps there are from a possibly singular Riemann surface of genus G to X, such that the number of times the image of the map wraps around the basis of curves is given by the tuple d. By the way, the tuple has to be non-negative because we're looking at holomorphic curves. So there is a preferred orientation there, right? And the number of such maps is the genus G degree D Gromov-Witten invariant, like in a certain rough sense. I'll not be more precise than that. Okay, so all of these Gromov-Witten invariants can be assembled into a generating series called the Gromov-Witten potential, which is denoted F hat over here. Now the grading over genera, it comes from powers of the topological string coupling lambda, while the grading over degree comes from weighting terms with the volume of the image with respect to the complexified Kähler form. It will be convenient for us to separate out the degree 0 part, denoted F0 here, from the rest of the GW potential, which is denoted F tilde. Okay. So next, let's specialize to the case of the resolved conifold. Now, as the name indicates, this is obtained by taking the conifold given by the equation Wx equal to Yz in C4 and blowing up the singularity at the origin. The result is the total space of a complex rank 2 bundle over the exceptional divisor. Alternatively, you can also think of it as what a Calabi out threefold looks like in the neighborhood of a copy of P1 sitting inside it, which is why mathematicians also call it local P1. Now, the degree 0 part of the GW potential is universal up to an overall factor, which depends on the Euler characteristic, which is 2 here. But the higher degree part was independently computed to be this expression by mathematicians Faber and Pandharipande and physicists Gopakumar and Vafa. Now, both of these expressions, they involve the Bernoulli numbers defined here, and these grow extremely rapidly. So both these series have 0 radius of convergence. So that might seem like a problem, but this is something that we'll come back to in a few slides. But before that, let's look at the...
Could you explain how this calculation by Gopakumar Vafa was done? Just the outline. If it's too outside the talk, then don't worry.
Okay, yeah. Let me actually let's talk about this like at the end, because I think it'll probably yeah. So from what I understand, they basically did a lift to M theory and did some computations there. But okay, but yeah, let me set this aside for the moment and continue. Is that okay?
Yeah, sure.
All right, so now let's look at the Donaldson-Thomas side of things. Now, DT invariants, they count certain generalizations of vector bundles called coherent sheaves, subject to a certain semi-stability condition. So without going into details, I will just give you the physical interpretation of what this means. So by coherent sheaves, I mean a charged brane wrapped around the holomorphic submanifold. Okay, and when I say that its Chern character is of this type, I mean that the brane has real dimension 0 or 2. And finally, by semi-stability, I mean that the branes are BPS. Now recall that BPS branes are extremal in the sense that they maximize the charge for a given mass. Okay, so well, this is an angle over here. It's an argument of some complex number. The cotan of this angle is the charge to mass ratio of the brane. Okay, so what this inequality is telling us is that the brane cannot increase its charge to mass ratio by decaying into something lighter. It is therefore semi-stable in a physical sense. The DT invariants count such branes with Maxwell-Boltzmann statistics, but for our purposes, it will make more sense to do the counting with Fermi-Boe statistics instead, and which gives us the BPS invariants. And this is just a repackaging of the DT invariants, and there is no information lost either way. You can get this from that and that from this. Okay.
When you say that the DT invariants count the things with Boltzmann statistics, what exactly do you mean? I mean, are they weighted by the Boltzmann?
Right. Yeah. So this interpretation basically comes from a paper from 2011. I think it's called Wall Crossing in Boltzmann Black Holes by Jan Maschot, Boris Piolin, and Ashok Sen. And basically, if you assume different statistics, you can. There are these two sets of Donaldson-Thomas invariants, which I'm calling DT invariants and BPS invariants, but they call it rational DT invariants and integer DT invariants. And basically, the statistics comes from the fact that if you have two of such brains, how are you really thinking of them? Are you thinking of them as distinguished objects, or like this is same thing if you swap it around? And that leads to different numbers, but they are of course related. You can translate between the two using this multi-cover formula, so to say.
Where is the statistics coming in? That's the question.
Because there are brains. I mean, think of the brains as some black holes. Yeah, okay. Think of a collection of black holes. Think of them as a gas of black holes, so to say. And then you can talk about if you have two black holes centered around two different points, and are you thinking of them as two distinguished objects? Like if you exchange the two, is that a different configuration, or is that the same configuration with? Yeah, so that's how the statistics comes. Does that answer your question?
Yeah, I guess, but why invoke black holes? I mean, you have just
because that's precisely what black brains are. Like holes are basically when they're basically zero dimensions of space, and this is like a higher dimensional generalization of that.
That's true, but why make them black? I mean, because they're BPS or something like that.
I mean, if you have any if you have any point object, for instance, the gravitational field around it will be that of a black hole, right? Like the only reason that the sun isn't a black hole is that the sun is too large, and the Schwarzschild solution stops before you actually get too far into the center.
No, all brains do not devolve to black holes. Only when they acquire too much mass do they become black holes. I mean, it's not necessary that a brain essentially is always a black hole, right?
Arpan, maybe is it relevant here to note that?
No, it's okay. It's not really relevant. So maybe, okay, all right, yeah, maybe let me.
No. I was going to say that there is I mean, you're talking about BPS objects. You can think of them as BPS particles in, I suppose, some 4D n equal to 2 theory, or there's a dual interpretation as some black holes in supergravity, right?
Yeah, right. Yeah, right. Yeah.
So maybe that dictionary is what is there in the background here.
Yeah, exactly. Yes, yeah.
Am I correct?
That's correct. Like, that's right. Yeah, depends on how you look at this. Yeah.
Yeah, maybe so that might help answering the question.
So is that okay?
Sorry,
I didn't get the answer. Can you just explain what that
meant?
No,
so the BPS objects appearing in Arpan's talk. So they have different interpretations, one of which is as BPS black holes in certain supergravity theories. You can think of them as also BPS objects in 4D n equal to 2 theories and so on, and there's a translation between these interpretations. I think the papers that Arpan was referring to, they basically work out this dictionary.
Yes.
Okay.
Yeah, right. Yeah.
Okay.
So, I mean, before you move on, I have a comment or question. I don't know if it's a question or comment, but I don't understand why you call these A-model invariants. You're talking about objects in the derived category of coherent sheaves.
Yes. Yeah.
And you're counting them.
Mm-hmm.
Why do you call them A-model?
Yeah, because the Gromov-Witten invariants are A-model objects, right? Like they are. Yeah. That's the A-model topological string theory, and these are the bound states of the theory, of the same theory. So there is no mirror symmetry or anything that I'm going to invoke here. So it's for that reason.
Yes, I don't know what that sentence means to say that they are the bound states of that theory. Can you explain that? I mean, you can explain
perhaps it will be a bit clearer if like the next few slides are going to be about this resurgence aspect of things, and maybe let's come back to this question at the end of that. But okay, if the problem is just what I'm calling the okay, this DT invariance, like A model DT invariance, then okay, it's just a question of the name. But
I agree.
But the whole point is that I'm never leaving this A model string theory. I'm not making use of any duality or anything, like no mirror symmetry, no S duality, nothing.
Well,
like
you're making use of the B model to describe the objects that you just defined on this slide, right? You're talking about, I mean, everything that's defined here is a B model object. You're counting.
Okay, again, when you say object, you mean object in a categorical sense, right? Like the thing that the arrows are in between.
Well, whatever sense, it's a boundary condition in the topological.
Yeah, so, but when I'm referring to holomorphic curves, I'm not referring to them as a boundary condition, but as a sort of like a charged object. It's not something that the strings are incident on.
That happens only when you get holomorphic curves only when you put this condition on the Chern character, right? But I can define, I can have higher dimensional objects supported, coherent sheets supported on like higher dimensional objects, for example. Those don't have any interpretation in the A model as far as I can tell.
Yeah, right, yeah.
So it's some arbitrary thing about choosing the Chern character to be 0, 0 and something. I mean, I don't understand. What is the statement relating A model bound states? First of all, what is an A model bound state to a mathematician in mathematical terms, and how is that related to this definition?
Right. Okay. So okay, let me discuss a bit about resurgence, and maybe I'll be in a better position to answer that after that part. Okay.
Okay. Yeah.
Okay. Okay. But yeah, before I move on to that, let me just mention that the BPS invariants of the resolved conifold, they are actually explicitly known. So if I denote the class of the zero section as beta and choose a generator delta for edge 0, then the only non-zero BPS invariants are basically -2 when the charge is of the form some non-zero integer times delta, and 1 when the charge is of the form plus minus beta plus some integer times delta. Okay, and well, the resolved conifold is a particularly simple example, and no wall crossing takes place, so there is no dependence on the Kähler parameter T. But in general, there can be a dependence, and the BPS invariants can jump across certain codimension 1 walls in the Kähler moduli space. Okay, so now, yeah, this is the bit about resurgence that I mentioned. So let's come back to the issue of the zero radius of convergence that we saw in the GW potential. Okay, so this is in fact the typical situation that you have in perturbative field theory. That the perturbative expansions, they have zero radius of convergence. But you can still make sense.
So to be clear, the GW potential is just an expansion in terms of the GW invariants, right?
Yes, yeah. The
with
genus expansion.
With some weighting factor.
Yeah, right.
Okay.
Okay, so even though such expansions, such perturbative expansions, they are not they don't converge anywhere, you can still make sense of them as an asymptotic series for some function. So what does that mean? So here's a definition of an asymptotic series. It says that if you give me some positive integer capital N and the half plane centered on some ray rho, then I can make this quantity arbitrarily small by choosing lambda in the inside the half plane and close enough to 0. Okay. Now this is to be contrasted with the definition of convergence, where you give me a lambda and I choose n to be high enough in order to make this difference without that extra factor, and to make this difference arbitrarily small. So it's in some sense the other way around here. But this doesn't completely solve the issue, because the asymptotic series doesn't uniquely fix a function A, unlike the case of convergence. So as an example, consider the zero formal power series. It is asymptotic to both the identically zero function as well as e to the power -1 by lambda. Okay, in the half plane centered on the positive real axis. Right? However, you can restore uniqueness with an additional
could you
growth
just
condition.
explain the previous statement that you just made? Could you just
Okay.
explain the previous statement?
So this statement at the end, you mean?
Yeah.
Okay, so the thing is that both the zero function, like if you put 0 over here, right, and if you consider this function e to the power minus 1 by lambda, both of them will satisfy both of them will satisfy the definition of this. Like, the zero asymptotic series. Like, if you put 0 here, then, well, okay. So if this is 0 and this is 0, then okay, this equation obviously holds as you take the limit lambda goes to 0 because this is identically 0. But if you take e to the power minus 1 by lambda here and 0 here, okay, and you fix some ray, once you fix a ray in the half plane which is centered on the positive real axis. So basically, the real part of lambda is greater than 0, and then once you have fixed the ray and you're taking the limit along that ray, then this limit will still go to 0, and that has to do with the fact that e to the power minus 1 by lambda, well, it decays. As you go to 0, it decays faster than any polynomial function.
If lambda goes to 0, then 1 by lambda diverges. So e to the
but e to the power minus 1, e to the power minus infinity is like 0, right? It decreases very quickly.
Yeah. So then
so basically it decreases faster than any polynomial can, and so this limit will still be 0 once you fix the ray in this half plane.
And how is that related to the definition of resurgence?
Okay, so the way it factors into this definition is that both the 0 function satisfies this. The formal power series, the identically 0 formal power series where all the ans are 0. They are an asymptotic series both for the 0 function as well as e to the power minus 1 by lambda. Right?
Arpan, I think the connection to resurgence would be clear if you move on.
Okay. Thanks. Okay, so basically the problem is that it doesn't uniquely fix the function, unlike the case of convergence, where if a series is convergent, then it converges to a unique function, right? But that isn't the case here. If something is asymptotic to some function, that function is not unique. There could be multiple functions that it's asymptotic to. However, you can restore uniqueness with an additional condition, an additional growth condition. So basically, if this inequality, which is stronger than the definition of an asymptotic series, if this inequality holds in some small disk inside the half plane whose boundary touches the boundary of the half plane at the origin, then that uniquely fixes A. Okay. Moreover, this unique function A can be explicitly obtained from the asymptotic series via a procedure called Borel resummation, which I'll explain on the next slide. Okay, is that fine? Right.
I am not sure what you exactly said, but you can go ahead. I mean, maybe things will clear up.
Okay. All right. Okay. All right. So Borel resummation has two steps. The first step is to perform a Borel transform. Now, this is defined for a power series where a formal power series where the lowest order is at least 1, and it involves including factorials in the denominator by hand. Now, you can see straight away that it improves the convergence. Okay, and in fact, if the bound in the previous theorem that I just showed you, if that bound holds, then this thing, in fact, has a non-zero radius of convergence. Okay, so you actually get an analytic function. It defines an analytic function by analytic continuation. Then, to obtain the Borel sum or the Borel resummation, you have to perform what is essentially a Laplace transform along a ray row. Note that if you had applied this procedure to a monomial, if there was no summation here, just a single monomial, then you would end up with the integral representation of the gamma function. Okay. Now at positive integers, that is just n-1 factorial. The gamma function is just n-1 factorial. And that would cancel out the n-1 factorial in the denominator, and it would give you back the monomial you started off with. So it gives the right answer for monomials. Like you get back the original monomial if you apply this procedure. And in fact, it works for convergent series in general. But now the nice thing is that the resulting integral makes sense as an analytic function, even if the series that you started off with didn't converge anywhere. Okay. So now you have taken this divergent series and assigned to it an analytic function. So that's what Borel resummation does. And it gives you, in fact, the unique analytic function that the theorem on the previous slide describes. However, as you may have noticed, that there is a dependence on the ray rho along which you take this Laplace transform.
So is the understanding that with different rays, the convergence wouldn't work out or something? And it depends on...
Yeah, so that's what I'll tell you. What happens if you do it along different rays? Okay, so here's a picture. If you perform the Borel resummation along, say, the blue ray, you get an analytic function which is in the blue half plane, right? Whereas if you perform the resummation along the red ray, you will get an analytic function in the red half plane. Now, if the Borel transform didn't have any singularities, these would agree. But the only situation in which the Borel transform doesn't have singularities is if the original asymptotic series was convergent to begin with, and you wouldn't need to do all these things. So in all the interesting cases, the Borel transform does have singularities. And in that case, like suppose the singularity lies on this green ray over here, okay? Then if you take the Borel resummation along two different rays on either side of it, then on the overlap of the common domain of definition of the Borel resummation, they're not going to agree. And this discrepancy is said to be the Stokes jump across the green ray, along which there are poles or branch cuts or singularities of any kind. Okay, and this discrepancy might seem like an annoyance, like that you just have to deal with, but it actually has physical meaning. It's not something just an artifact of the maths as such. It does have a physical meaning. And I want to show you an example to illustrate this point, which will hopefully answer Pranav's question as well. Okay. So here's this quick example. Well, consider a zero-dimensional QFT over a single point with a single real-valued field, var phi. Okay, so the configuration space is just the real line. The action functional is an ordinary function of a single variable, and the path integral is an ordinary integral. Okay. Now the perturbative expansion about the vacuum via Feynman diagrams amounts to expanding e raised to the quartic term into a series, the usual series of the exponential function, and then doing this integral term by term. The result gives you an asymptotic series for the path integral with zero radius of convergence. Okay, now you have an asymptotic series. Now you can do the Borel transform. The Borel transform of the non-constant part is given by this expression, which involves the hypergeometric function 2f1. Okay, and this has a branch cut which runs from -infinity to -1/16, and the Stokes jump, which is basically some kind of a Laplace transform, right? And the Stokes jump, the Borel resummation is a Laplace transform. So the Stokes jump is the difference of two Laplace transforms. So that is given by a Hankel contour integral around this branch cut. And
I have a question.
Yeah.
Like, is the understanding that the Borel transform actually gives you back the original polynomial along some specific ray, and it still matches with the original expression at the origin? Is that correct? At the origin, where you had this initial, this 12, the equation 12.
Okay, so if you are just given a polynomial or even a convergence series, okay, and you perform this procedure, like you first take the Borel transform, and then you take the Borel resummation, yeah, it will give you back the original series. That is correct.
Yeah.
So
is the understanding that if you now work with the Borel transform, then things get simplified, but you're working in the complex plane instead of the real axis. Is that correct? I mean, you're complexifying
yeah, right. Yeah, okay.
the lambda.
You can think of it like that. Yes, yeah.
Okay.
I mean, it assigns a meaning to something which doesn't have meaning per se, like an expansion which converges nowhere. That seems to have no meaning, but it allows you to assign a meaning to that, an actual function to that. Okay.
Yeah, I mean, I guess if it allows you to compute things, experimental values or experimental numbers more easily, then I guess it has a utility. So go ahead.
Okay, maybe I should mention that. Okay, in experimental situations, actually, it's enough to consider the first few terms and then stop. And there's a reason for this. Like there's something called optimal truncation, and you can show that if you truncate at the right point, then the difference of the truncated version and the Borel resummation is actually of the form e to the power minus 1 by lambda, that kind of thing. And so basically, when lambda is small enough, it decays so quickly that you can virtually see no difference. But this does have utility beyond just assigning a nice function to things.
But the truncated series necessarily, I mean, the truncated series doesn't have problems with radii of convergence and things of that sort. Isn't that true? I mean, when you consider the infinite series only, then do you have the problems with radius of convergence going to 0 or something like that, right?
Yeah, right. Yeah, that is right. Yes.
So I guess this entire framework is devised to consider the full series. I mean, the full.
Yeah, exactly. It's devised to consider the full series. Like if you just care about the first couple of terms, then then there's no point to doing it.
Yeah. Okay. Good.
Okay. Right. Okay. So the associated Stokes jump across this branch cut is of the form e to the power 1 by 16 lambda times some meromorphic function. Okay, so what's the physical meaning of this? Okay, to see that, first we carry out a change of field variable from var phi to phi. The point of this change of variable is that the integral for the path integral is well defined for non-zero complex values of the coupling lambda. Previously it wasn't, but now it's well defined for all non-zero complex values. And then this integral can be approximated by the method of steepest descent. Okay. So in order to use that method, first we have to let the field variable phi, the new field variable, we have to let it be complex. So that will give us two new critical points of the solution. Okay, so these are the two new critical points, and these are the classical instant-on solutions. So what Borel resummation does is that it isolates the contribution from the steepest descent contour integral through the true vacuum at 0. So when the decomposition of the real line, that's the integration contour over here, when that decomposition changes from this to this, as lambda crosses the negative real line, then you get a discontinuity, because this is the analytic function, but isolating just the contribution from the steepest descent contour through the true vacuum, that's not analytic. So you get a discontinuity, and that discontinuity is exactly going to be the contributions from these steepest descent contours, which are going to be of the form e to the power minus the action. So that is e to the power 1 by 16 lambda times some meromorphic function, right? And that is exactly what we got from the Stokes jump. So what we learn from this is that Stokes jumps tell you about instant terms or bound states in the theory. So there is like a true vacuum, and there are these hidden non-perturbative states. So this is what I'm referring to when I say bound states. So does that sort of answer your question, Pranav? So this is bound state in the sense of instant-on solutions that you might encounter in the context of Yang-Mills.
Yes. So, but how does this answer the question about the dependence of the? See, you define something using the derived category. I think maybe the resolution is really that the DT invariants you depend on the derived category of coherent sheaves, but they also depend on the Kähler parameter because they depend on the stability.
Yeah, okay. Right, yeah. So in this particular example, you don't see that dependence, but yeah, in general, it should.
Yeah.
I guess you have to frame the this entire story in terms of A model, B model statements, right? I mean, those are field theories. I mean, those are topological field theories. This is just zero plus zero dimensional quantum mechanics.
Yeah. So this is just an example. This is just an example to illustrate something I'm going to do with the A model. Okay. So basically, the next thing I'm going to do is apply this whole machinery of resurgence that I illustrated using the zero-dimensional QFT to the Gromov-Witten potential, which is the perturbative series for the A model, right? And I want to do the same thing there. And just as we got access to the non-perturbative sector of the theory given by the classical instant-on solutions in the zero-dimensional QFT case, we expect to get something similar in the A model case as well. And that will have information about the DT invariants.
Yeah.
Okay, so is that okay? So that's basically the idea. Okay, so I guess if that's fine, now we'll basically apply, this is the second part of the talk where I'm going to apply all this stuff to the GW potential. Okay. So in order to apply this machinery of resurgence to the GW potential, we'll be needing a special function that was featured in a recent paper by Bridgeland on the resolved conifold. Now it's related to the standard triple sine function with repeated argument by a factor of the form e raised to some polynomial. So, and since they're very closely related, I'll just be calling this function Bridgeland's triple sine function, okay? So I'll define this function through this integral formula, which is valid in a certain range of the arguments. And then I'll extend it beyond that range through analytic continuation. So that means that, for example, from the integral formula, it's clear that this rescaling property holds when A is in the neighborhood of the positive real axis, because you just have to rescale the integration variable, and that shouldn't change the result, right?
Sorry, because what is this Bridgeland's triple sine function? How is it related to the DT invariants?
Yeah, so that's precisely what I'm going to say. But the thing is that this is a function I'll be making use of in what is to come. So I'm introducing it, and I'll make use of this function, basically. So in some sense, this will describe the non-perturbative description. This will be the non-perturbative description of the topological string-free energy in a certain sense. So that's why I'm introducing this function. Okay, so and that's the definition. Like I'm not doing so far. I'm not done anything. I've not made any claims. I've just introduced a certain function that I'll go to make use of. Yeah. Yeah. So just to illustrate something that, okay, this equation certainly holds for a positive real number and something in the neighborhood of the positive real axis. So that you can conclude from the integral formula itself. But since we're defining it through analytic continuation, this will hold for all all non-zero complex numbers A. So, okay, so now that we've defined it, so we first turn to the task of Borel resumming the non-zero degree part of the Gromov-Witten potential, which is denoted F tilde. Now, recall that the Borel transform is only defined for formal CDs where the lowest order is at least 1. So accordingly, I define a function phi t which is basically just F tilde, but with the genus 0 and genus 1 contribution removed. Okay. So that the lowest order thing, okay, now it's 2, but there is no constant term and there is no term of the order -1. So that's the point of this. Now, given that, we have the following result for the Borel transform. It turns out to have an explicit series description. And from this description, you can read off what the poles are. Okay, so the poles are basically, for a fixed value of t, the poles are at xi equal to 2 pi I t plus km, where k is some integer and m is a non-zero integer. Now, let me show you a picture of this. So again, recall that this is for a fixed value of t, and this is the xi plane, okay? And on this plane, you have infinitely many poles along each of the dotted rays over here, and infinitely many dotted rays accumulating on the imaginary axis. So this is called the peacock arrangement because it is supposed to remind you of the patterns on the tail of a peacock when it fans out the tail. I don't know if you might see it, but yeah, that's why it's called the peacock pattern or peacock arrangement. Now, the dotted rays are labeled plus minus LK, K running over all the integers. For carrying out Borel resummation, I'll need to choose some rays along which I take the Borel resummation, right? And these will need to avoid the poles. Okay, so I choose the rays plus minus rho K with K running over the integers such that rho K lies in between LK minus 1 and LK. So in particular, rho 0 may be taken to be the positive real axis if the real part of T lies in between 0 and 1. Right, so these are the rays along which I'm going to take the Borel resummation. Okay, it then turns out that the Borel resummation
so along that
rho
ray,
K,
there are
sorry?
singularities.
Sorry?
Along that ray, there are no singularities along the ray which you are taking. Are there no singularities?
No, because the singularities are along the dotted rays, and I've deliberately chosen my solid rays, the rho K, so that it avoids those singularities. So
Okay.
I'm choosing them between them.
So the understanding is that if you take your Bridgeland series and expand in terms of expand as you have expanded, then along those rays there are no poles. That's what you're saying, right? But
yeah.
I would be a bit surprised because if you go back to that previous form, I would presume, yeah. So this this form,
right. The poles are basically of the form 2 pi I t plus k times m, right?
Right.
And basically these rays LK, the dotted rays, they're defined by they are basically defined by some negative real number times 2 pi I times t plus k.
Correct.
So that means basically the poles will be lying along these rays, right?
Which rays?
Along the dotted rays.
Yeah, how do you define? I mean, so
okay, the definition is basically this. Like, so the poles were of this form, right? So there was this integer m involved, a non-zero integer m involved. So I'm basically defining the dotted rays to be 2 pi I times t plus k times the negative real numbers.
Correct. And
so that will give me the dotted rays. So the poles will be lying on these dotted rays.
And t plus k would determine the slope of the rays. That's correct, right?
Yeah, right. Yeah.
So I would assume that t plus k would be some non-zero number for any of the rays, right? I mean, why should they be why should they be zero for some particular ray? In that case, if it's not zero for some particular ray, then there wouldn't be the fact that there are no poles along that ray, right?
No, there are poles along the dotted rays.
Along dotted rays, but along any ray, isn't t plus k unequal to 0? Why should t plus k be not equal to 0 along row 1, for instance?
Because Okay, t is a fixed complex number, right? Like, which is basically the Kähler parameter. I'm fixing a value of t.
Okay.
And this is basically the psi plane.
Yeah.
I mean, this is basically just psi. I'm not showing you t. Yeah.
Yeah.
So I fixed t. Okay, so this is just a fixed complex number. And then I basically the poles are giving me a bunch of complex numbers in the xi plane, right?
Yeah.
So basically you can see that there are infinitely many poles given by, if you vary just m, like say you fix k and you vary m,
Yeah.
then you will get like infinitely many poles along lk.
Right. Now,
and then you vary k, then basically you generate this entire pattern, like, with all the lks. And the poles are basically just on these rays. On this
now go back to the previous slide, please.
Yeah.
Yeah. So here, if this factor, exponential factor, if the coefficient in the exponential factor was always 0, for instance, then I would presume that you have a pole only at the origin and nowhere else, right? Isn't that correct?
I mean, in general, it can be of it can be 2 pi I times some integer, right?
Yeah, I'm just trying to see how you can have no poles along some specific ray.
Okay, all right. So suppose, I want this to be 0.
Yeah. So
then in that case, if you solve for
1 minus 1, and so you just have a single pole at the origin, isn't that? Wait.
But why the origin? Like, you want this entire thing to be 0, right? And then you can solve for xi. And if you solve for xi, this is what you will get: 2 pi I tm.
No.
In that case,
that you get for a specific case. I mean, for an arbitrary case, that would give you the poles. But what
I'm fixing t. So basically, t is supposed to be fixed in this case.
Yeah.
So think of this as some constant. Okay. And now I want to solve for this being equal to 0, this denominator. In other words, I want to solve for this thing being 2 pi ik. Right. So now I set this equal to or minus 2 pi ik.
Right. So now the question is sharp. So in order to have no poles along some ray, there should be no solutions to the equation 2 pi it plus rho xi by m equals 2 pi k. There should be no solutions to that equation.
Yeah, but okay, I'm solving that equation here, right? Like psi is equal to 2 pi I. Yeah. So basically, I found all the solutions.
I think for fixed t, it's clear what Arpan wrote. Like, if you choose rho k to lie between lk minus 1 and lk, right? That is a way to pick a gap where there are no poles, and that's basically, he's picked one such gap. You could pick other ones, I suppose, if you want to.
Yeah.
I think it's clear for fixed t that you can pick such a rho.
Okay, so is that clear? Shall I move on?
Yeah, I think you should move on. And maybe we will let Arpan go on, and we can reserve like questions for the end. You can take how much of a time.
Yeah, so there'll actually be a natural break before I get into the geometric interpretation, and maybe I will take questions at that point.
Yeah,
perhaps.
Yeah. I mean, if there are like urgent clarifications, but otherwise,
sure.
like longer discussions, maybe we'll push it to the end.
Okay, all right. Okay, so I've chosen my rays rho k, and then the Borel resummation along rho k, the Borel resummation of f tilde along rho k is basically log of Brisland's triple sine function with the argument t shifted by k. So that is why I had introduced this function at the beginning of the section. Okay, because these are basically the log of this function with the argument shifted by k. That's basically the Borel resummation. And the Stokes jumps are given by this expression, which involves the dilogarithm. Okay, so that's Borel sum and the Stokes jumps. Okay, so this was for finite values of k, but it turns out that I can sensibly take a limit of k going to plus or minus infinity. Like, I have all these expressions for a finite value of k, and I can take the limit of that for k going to plus and minus infinity. And in that limit, this is what we are going to get. So we get, in both the plus minus, k going to plus minus limits, we get this expression for the Borel resummation. And you might recognize this as the Gopakumar-Waffa resummation. Moreover, the sum of all these Stokes jumps that you need to go through in order to get to this point, it also has an interpretation. So this is the expression that you will get. And this thing in the bracket over here is the Nekrasov-Shatashvili limit of the refined topological string. So let me put this in a slightly more familiar form there. Now, I will not delve into any more details, but I will just note that this proposal that the non-perturbative definition of F tilde should be taken as this particular combination of the Gopakumar-Waffa resummation and the Nekrasov-Shatashvili limit is due to Hatsuda, Marinho, Moriyama, Okuyama. And it's nice to see it pop out in a natural way from our approach. Moreover, it suggests that the ray rho 0 is distinguished because it's only the resummation along that ray which has this decomposition. Okay. But we are not done yet. We still have to take care of the degree 0 part, F0. And for that, again, you can play the same game. And in fact, the Stokes rays that you get in this case can be essentially obtained as a careful limit of the peacock arrangement as t goes to 0. But the limit is taken in such a way such that the distinguished ray rho 0 remains unchanged. Anyway, so these are the Borel transform and Borel resummation along rho 0 that you obtain. So this is expressed in terms of the Borel transform and resummation for the non-zero degree case, but you basically set t equal to 0. And that's a well-defined limit. And so this is a well-defined quantity over here. And the Stokes jumps, well, these are the Stokes jumps. Again, the Stokes jumps are only across the positive and negative imaginary axis, and they can be given in terms of the Stokes jumps in the case of F tilde. Okay. So basically, again, you set t equal to 0 here, and that will give you the Stokes jumps across the positive and negative imaginary axis for F0. So that was the Stokes. Those are all the Stokes jumps. And how to retrieve the BPS spectrum from this? Okay, so to retrieve the BPS spectrum, you look at all the Stokes jumps for the full Gromov-Witten potential, that is F hat equal to F0 plus F tilde. And then you can read off the BPS invariants from the prefactors of these expressions involving the dilogarithms. Okay, so this is the charge of the BPS state, and this is the BPS invariant that comes in front of that. And what we have done here is roughly the inverse of Bridgeland's solution of the Riemann-Hilbert problem associated to the resolved conifold. Now, whereas Bridgeland started with the BPS spectrum and then constructed functions whose asymptotics and Stokes jumps encoded that BPS spectrum, we started with an asymptotic expansion and read off the BPS spectrum from the Stokes jumps. Okay. And let me also reiterate that the resolved conifold is an example where things simplify considerably. In general, we should expect that the arrangements of the Stokes rays will be dependent on the Kähler parameter, and the places where the Stokes rays coincide are the co-dimension 1 walls on the complexified Kähler modular space. And as you move across those walls, new Stokes rays may appear and old ones may disappear. And that is what basically wall crossing is. Okay, so now we basically come to the final section. And in this section, what I will discuss is that the ambiguity in the non-perturbative definition of the Gromov-Witten potential that comes from Borel resummations along different Stokes, along different rays. So that ambiguity can be geometrically interpreted in the context of the supergravity C map, and that's what I'll be telling you about next. So we'll shift gears slightly here. So maybe if there are any questions about the part I just covered, maybe I can take some of them now.
So the comment about the Nekrasov-Shatashvili limit, so should I think of some particular 4D n equal to 2 theory, and there's some analog of omega background, and this is a particular limit in that? Or, I mean, if these details are not pertinent, then we can move on. Okay,
so yeah, the topological string of the, on the resolved conifold, basically. So if you want a specific thing in mind.
Okay.
Okay, so, I guess I will move on then.
So is the understanding that you have got this relationship with the Gopakumar, Vafa, and Nekrasov, Satashvili by just inventing this particular Bridgeland function and taking the expansion and getting the poles and expanding in terms of that? Is that correct?
So, okay, so this Bridgeland triple sine function, that's something that sort of naturally comes out. I mean, there were no artificers involved there. Basically, I have the Gromov-Witten potential, and I perform this general procedure called Borel resummation, and I got these functions from there, right?
Okay, so yeah, go ahead.
Yeah, and then I can take the resummation along any ray which doesn't contain poles. Okay, let me perhaps go back to that. Okay, so in particular, okay, so all of these dotted rays, they accumulate on the imaginary axis, but there are no poles on the imaginary axis. All of these things accumulate there, but there are no poles on the imaginary axis itself. So you can take the Borel resummation along the imaginary axis itself, but you have to be a bit careful, of course, because there are these rays are like dense around the neighborhood of that. So the way you do it is basically you do it by taking a limit of what the Borel resummation along a ray here would be, what it would be here, and then you can basically define a sensible limit, and it gives you a sensible answer. And that's basically the Borel resummation along the imaginary axis. And so what we are saying is that Borel resummation is the Gopakumar-Vafa resummation. And everything and all the Stokes jumps that you have to go through to get from row 0 to that ray is given by the Nekrasov-Shatashvili limit of the refined topological string.
How are you doing integral? Because there are poles along the imaginary axis, I guess. So how are you doing it?
There are no of F tilde. There aren't poles along the imaginary axis.
Okay, so but this is like the diagram. It seems that they're all dotted lines, right, along the imaginary axis. Aren't the dotted lines?
So the dotted lines are crowding around the imaginary axis, but at t equal to 0, yes, but if t is different from that, then there aren't. Because in order to, let me remind you that the imaginary part of t is positive because it's a Kähler parameter, right? Like you want a Kähler manifold. So the imaginary part of t is positive, and in order for a pole to be there on the imaginary axis, basically t would need to be a real number, but that is excluded.
Why is that excluded?
Because so this is how t was let me see what definition of t is. Sorry. Just a minute. The t was defined as basically like you have this sorry, just a minute, let me right here. So the complexified Kähler form is minus b plus I omega, where this is the Kähler form, the real Kähler form, right? And the fact that there's positive definite means that if I integrate omega over any curve, any complex curve inside the Calabi or threefold, then that's going to give me a positive volume.
Yes,
right?
yes.
So if
Yes.
I integrate omega c over any complex curve, then the imaginary part of the result is going to be positive.
Yes.
And that's what t is. Like, it's the integral of this over a complex curve. So the imaginary part of that has to be positive because of that.
Okay.
Okay, so yeah, basically that's why there are no poles on the imaginary axis. But the limit of t going to 0 is well defined. And that's the limit that we make use of for doing the Borel resummation of the degree 0 part. Okay, so I guess that's all for the previous section, I guess. Okay, so let me continue with the rest. So, okay, so what I want to do in this section, as I mentioned before, is I want to interpret the ambiguity in the non-perturbative definition of the GW potential in a geometric way in context of the supergravity C map. So, which is what I'm going to tell you about. So first, let me start with the broad picture. Now, scalar fields in a supergravity theory can be thought of as coordinates on a pseudo-Riemannian manifold of scalars S. Okay, so a scalar field configuration would be given by a harmonic map from 4-dimensional spacetime to S. Supersymmetry then implies constraints on the geometry of S. So the two cases that be of interest to us are firstly 4D n equal to 2 supergravity coupled to vector multiplets, in which case S is equipped with a projective special Kähler structure. I will tell you what that is in the next few slides. And secondly, we have 4D n equal to 2 supergravity coupled to hypermultiplets, in which case S is quaternary Kähler. Now, we can dimensionally reduce the 4D n equal to 2 supergravity coupled to vector multiplets to 3 dimensions, and then lift it back again to 4 dimensions to get a 4D n equal to 2 supergravity coupled to hypermultiplets. The scalars of the hypermultiplets consist of scalars from the original vector multiplets, plus some new scalars which come from the vector fields of the vector multiplets. So, and this is called the supergravity C map. And what this should give us is a geometric construction that takes as input a PSK manifold and gives as output a QK manifold, forming a bundle over the PSK manifold.
Sorry, can I ask a question?
Sure.
What does it mean to lift? I understand what it means to dimensionally reduce. By the way, if it helps, I'm a mathematician. If it helps to frame the question, I mean,
so
for you to frame your answer.
So by lifting, I mean that you just introduce an extra direction and just say that the fields don't depend on that extra direction. Like you have some scalar fields in 3 dimensions, and then you can think of it as just a 4-dimensional theory, but the scalar fields don't depend on the 4th dimension.
Mm-hmm. Okay.
Okay, so in the context of, say, type 2 string theory, this is T duality. And we will see that the Stokes ambiguity that we encountered in the last section is a crucial ingredient for the de-instanton corrected version of the story. So the plan for the rest of the talk is, first, I will tell you what a PSK structure is and how GW invariants fit into the picture. And then I'll discuss a simpler version of the C map without de-instanton corrections. And finally, I'll tell you about a result relating the de-instanton corrected version with the Stokes ambiguity. By the way, Ashwin, how much more time should I take?
I mean, we have had discussions, say 10 minutes or so. You think that's practical?
Okay, let me say, I mean, I could skip some things in between, but
yeah, approx 10 minutes, I think.
Okay. So Okay, so let me skip this slide then. I'll just directly define what the PSK structure is so that you have some idea about what I'm going to talk about. Okay, so a projective special Kähler structure on a pseudo-Kähler manifold involves well, a certain real vector bundle E over it. And that bundle has to have a certain decomposition. Okay, so this decomposition is in terms of a complex line bundle L. And there has to be a certain pairing on this thing, a symplectic pairing, which is given in terms of a Hermitian form, HL, on the line bundle L, and the Hermitian form associated to the Kähler metric, which is HM. Okay, and this also has to have a flat connection, nabla, on E, and it has to satisfy a certain condition on the. So basically, what this is telling us is that if I take the covariant derivative of a section of L, which is living in the 3,0 part of this Hodge decomposition, I take the covariant derivative and then I project it onto the 2,1 part, then I get basically the tensor product. And there's something similar for taking the covariant derivative of something here and projecting it onto the 3,0 part. Okay. The physical intuition behind this decomposition, by the way, is that L is supposed to be the vacuum bundle, and L tensor T10M, L tensor the holomorphic tangent bundle, that is supposed to be the Hilbert space of states that you get by acting on the vacuum by holomorphic deformation operators. Okay, and right. So given that, like I can actually write there an explicit for expression for the flat connection that I just mentioned. So, okay, firstly, okay, I didn't show you the definition of a variation of Hodge structure, but it turns out that if you make use of that definition, then nabla will induce a holomorphic structure on L, and you have a Hermitian form HL, and you have a holomorphic structure on L. So that means that you have a Chern connection on L. And in terms of the Chern connection, the flat connection that I just described, that I just mentioned, will take this particular form. And this is in fact something that appeared in the BCOV paper on Kodaira-Spencer gravity, but written in a slightly different notation. Okay. So, so most of this flat connection is actually fixed by all the ingredients of the PSK structure, but there is this extra thing here, which I'm calling the deviance, and that plays the analog of the difference tensor that you might see in a fine special Kähler geometry. Okay, but let me not go too much into the details of this. But the point is that you can describe this geometry in terms of something called the prepotential, where in my setting, I'm thinking of the prepotential as a section of L star tensor L star, where L is this line bundle that I had just described. Okay, and you can get back the usual notion of prepotential that I think is more customary in physics by going to the total space of this line bundle L. Yeah, and then you can plug in the tautological section. The tautological section is an analog of, say, the Euler vector field on the tangent bundle or the Liu V form on cotangent bundle, but it's a very general construction that you can do for any bundle. So using that, you can basically get a holomorphic function on the total space of L, which is homogeneous of degree 2. Okay, and this prepotential will be useful in for describing deformations of a PSK structure. So now let me just show you a very quick example just to motivate the PSK structure. This is in fact the motivating example. So this is the example of the B model PSK structure, in which case like the PSK structure is defined on the complex structure deformation of a compact simply connected Calabi threefold. Okay, and you have the usual Hodge-Dolbeau decomposition, the polarization of the variation of polarized Hodge structure that is given by just the wedge product, and the fact that it satisfies the conditions of the definition is because of the fact that all of the three forms are primitive, because we assume that this is simply connected. And then you have the Hodge-Riemann bilinear relations, which guarantee that this in fact satisfies the conditions of the definition. And you also have a flat connection, which is basically given by the Gauss-Manin connection, and the pairing Q is parallel with respect to that. And in fact, you can see that this is a PSK structure. So a PSK structure was a special case of a Hodge structure, as a variation of Hodge structure, as I mentioned. So that follows from the fact that by definition, S3, 0 of a Calabi threefold is equal to 1. So basically, H3, 0 forms a line bundle. And then you have the Kodaira-Spencer map, which identifies L tensor, the holomorphic tangent bundle, with H2, 1. Okay. And then the Hermitian form HL is just given by the natural pairing. The Kähler metric is given by the Weil-Petersen metric. And this quantity deviance that I mentioned is basically just a Yukawa coupling. And the prepotential is then, for defining the prepotential, you need to make a choice of cycles. And once you have chosen that cycles, you have this explicit expression for a prepotential. So you can see that there's a section of L star because it takes into holomorphic volume forms and it gives you a number. But if you go back to if you pull back to the total space of L, then this will give you a function. Basically, if you consider the space of Calabi threefolds, complex structures on Calabi threefolds, along with a choice of holomorphic volume form, yeah, this is a function of a holomorphic function which is homogeneous of degree 2. So that's basically the idea behind the definition. But as it turns out, you can also define an A model PSK structure. So, okay, in that case, okay, I will not go through the details of this thing, but let me just say that the deviance is just given by the triple wedge product, and the prepotential is just the complexified volume form, the complexified volume of the Calabi threefold. Okay. And in fact, the flat connection can be written in a very nice way using the Lefschetz operators. If you make the identification with the, like you can identify E with the even cohomology, and then you can write down the flat connection in a very nice way in terms of the Lefschetz operators. So what I just described was the classical A model PSK structure, but it gets corrections from Gromov-Witten invariants. Basically, it gets corrections from genus 0 GW invariants with marked points. And this will basically deform the PSK structure so that instead of the wedge product, you have this big quantum cup product. Okay, so instead of the cohomology ring of the even cohomology is deformed to the big quantum cohomology ring, and you retrieve the classical A model PSK structure in the large volume limit when the imaginary part of omega c goes to plus infinity. So this just involves the genus 0 GW invariance. Okay, so you might ask, what about the higher genera genus, the higher genus GW invariants? Well, they form sections of not of L star square, which is where the prepotential lives, but they form sections of L raised to 2G minus 2. And so they can't be incorporated into the PSK structure. But if you go back to the total space of L, then this combination does define a holomorphic function on the total space of L. So basically, I'm interpreting the inverse topological string coupling lambda inverse as basically giving me the point on the holomorphic line bundle L. I'm identifying it with the tautological section. Okay. Okay. So all that description was for compact Calabi threefolds. the resolved conifold is not compact, but there are ways to repair that. For instance, you can make use of equivariant cohomology, and then you can use equivariant localization to basically have well-defined integrals. But it turns out that the details are not really important, because the GW expansion for genus greater than or equal to 2 is completely unaffected by all of this. Okay, and so the resurgent analysis that we did, which took into account only genus greater than or equal to 2, so that is completely unchanged. And so the Stokes ambiguity, the way you can resolve it is by thinking not of the Borel, but thinking of the Borel resummation as not a function on the total space of L, but a section of a certain line bundle. And basically the line bundle is chosen in such a way such that its transition functions are basically the exponentials of the Stokes jumps. So that means that e to the power f hat, or the Borel resummations of f hat, basically define a global section of this line bundle. Okay, and yeah, physically that should correspond to the Gromov-Witten partition function. And it is this line bundle on the total space of L that will play a role in the C map. So very briefly, okay, let me just, perhaps let me just skip this. Okay, so as I mentioned, the C map is something that should take in a PSK manifold and give you a quaternary manifold as a bundle over it. If you ignore the d instanton corrections, then the C map can be basically realized as a certain bundle over the PSK manifold, which is basically very explicitly given in this explicitly given here. This is just the fiber product of the VPHS bundle E and some tensor power of the line bundle, but with a certain tubular neighborhood of the 0 removed. And then there's a very explicit metric that is defined on that. But this will get some deformations from the d instanton corrections, and it turns out that you can define the d instanton corrected metric either in terms of a quaternary Kähler metric or a hyperkähler metric with a circle bundle P on it, with a connection that is of such that its curvature is of type 1,1 with respect to all 3 Kähler structures of the hyperkähler metric. And the way to and a recipe for constructing such d instanton corrected metrics was given by Gayotto, Moore, Knightsky. Basically, they showed that this is encoded in solutions to a very complicated system of integral equations, which look like the thermodynamic Bethe-Ansatz. And the hyperholomorphic circle bundle that I just mentioned was incorporated into the picture by Alexandrov, Persson, Piolini, Saueresig, and Van Doren. Now, given all of that, there is a conformal limit that was defined by Gayotto. This is analogous to the conformal limit in the thermodynamic Bethe-Ansatz, and it generalizes the Opel limit in the Hitchin moduli space, which by the way is a special case of a hyperkähler manifold which has a hyperholomorphic circle bundle. And what that geometrically does is it selects a section of the tangent bundle of the total space of L with the 0 removed. But this was precisely the space on which the Gromov-Witten line bundle LGW was defined. And the final result is basically that this GW bundle can be identified with the associated line bundle of the d instanton corrected hyperholomorphic bundle P in Gayotto's conformal limit. Okay, so that is basically all the results I wanted to discuss for today, and I want to leave with a few questions. So the first question is that that can this story be generalized to uncoupled BPS spectra in general? So the result conifold was this example where no wall crossing takes place. So can we say something in general for all such examples in which there is no wall crossing? So that's the first question over here. The second question is that, is there a direct global construction like we had for the version of the C map without de-instantons, but which generalizes to the de-instanton corrected case as well? So that so the idea is that we expect there to be a global construction whose input is basically a PSK manifold, along with a Gromov-Witten line bundle and the Gromov-Witten partition function, and it will output a de-instanton corrected quaternary metric. And a very similar construction was given by Bijland and Strahan, but that was in a slightly different context. So the input there was a complex symplectic manifold plus some Plebanski potential, which encoded the BPS spectrum. And so a natural question to ask is that what is the relationship between these two constructions, if there is any? And we would like to understand that in the future. Yeah, so that's all I wanted to say for today. Thank you for your attention.
Thank you. Thank you, Arpan. Let's thank the speaker. Yeah, so please go ahead if there are questions. You can either raise your hand or unmute yourself and ask. I guess there is a question. Yeah, please go ahead, David.
Yes, I have a question and a comment. My name is David Sauzin. As a matter of fact, with a colleague in Pisa 20 years ago with Stefano Marmi, we had studied a family of Q difference equations with a motivation from dynamical systems. But I'm very happy to see that, in fact, the very same object reappear here in the context of topological string theory. We were aware, and we mentioned something about the quantum logarithm in our introduction.
Right,
to
right, yeah.
Paper.
Yes, yeah.
And well, recently I noticed the paper by Garoufalidis and Kashayev, and your paper, in a sense, uses analogous mathematical tools. For instance, if I understand correctly, your Bridgeland triple sine function plays a role analog to that of Fadeyev's quantum D-logarithm in their paper.
Yes, exactly. So basically, the techniques that we used in the proof are directly inspired by Garoufalidis and Kashayev, and basically we cited them. So the idea, okay, the idea is that I can very briefly show you. Okay, wait. By the way, these are the extra slides. I wasn't intending to actually have them as part of the talk, but I had the. Just a minute. Okay, this is for the Borel transform. Yeah, right. So basically, this is basically the idea that you have in this Garoufalidis paper, where you think of this. You basically obtain a different expression for the dilogarithm, and basically the idea that you use to do that is you interpret this as a norm of two functions, the L2 norm of two functions, and then you use the unitarity of the Fourier transform. And that's basically what we did in order to
so you identify,
do the Borel resummation.
You identify one of the Borel Laplace sums, one with the ray rho 0 with the logarithm of G3 at the end of the page. Yeah. So that's interesting, because in our case with Stefano Marmi, we were more focused on the summation on the imaginary axis, because you have a channel, you have a vertical strip which is singularity free, because as you mentioned, the singular rays are just given by, you can take m equal to plus or minus 1, and you see that you have two lines of poles, and then you have all their multiples, but you still have a strip in the middle. And if you consider the Laplace, Borel Laplace in that direction, then for us, that was the natural solution. as I understand here, it recovers the Gopakumar-Vafa summation.
Yeah.
So which is, it's a remark here, it's the only resummation which has the property of being one periodic in variable t, because all the other summations are not, I mean, although the Borel transform is meromorphic and periodic in t, when you take the Laplace summation in one direction and when t moves, the Laplace direction moves. So this means that all your resummation, non-vertical ones, are analytic continuation one of the other with respect to t.
Right, yeah, that's right.
So in a sense, you have only, I would say, three Borel Laplace sums. You have the superior imaginary one, the negative imaginary one, and it's only one function that you have.
Yes, exactly. Like you can get that by shifting t. Yes, that's a pretty interesting remark, yeah.
And for us, the tools were completely different. We were only exploiting the Q difference equation. Q would be exponential of 2 pi I lambda check. So lambda check is your resurgence variable.
Right, yes, yeah.
And we were interested in, yes, in that problem for different reasons. And in fact, you can do the same analysis when lambda check is going to something different from 0. If it's going to any rational number, because this upper resummation is analytic on the upper half plane.
Right,
so
yeah.
The real axis is a natural boundary. And you have modularity-like properties. You can go to any rational, not only the origin, and you have relations which are measured by the Stokes jumps.
Maybe I should make this comment that, that although in the results of the paper that I just described, we don't really say anything about difference equations, but prior to this set of papers, there was actually a paper by Murad Alim on which involved using difference equations to say something about the non-perturbative definition of the free energy. And so basically these were there in the background, even though they aren't really mentioned in this particular paper, but that's exactly the things that led us to it.
Oh, okay.
So yeah. But thanks for the comment.
And one extra remark, if I may, very short. At the very end, you are interested not so much in the Borel summation, but rather in their exponentials. You are considering the partition function, the Gromov-Witten partition function will be the exponential. I don't know if you are aware that the exponential of a resurgent series is always itself resurgent. So here you are very lucky, because we are very lucky to have an explicit meromorphic Borel transform. So we can see the resurgence, we see the pattern very clearly. We only have poles, we can compute residues, etc. Of course, when you consider the exponential of that series, the Borel transform will be hugely ramified, but it is still resurgent. It's still endlessly continuable in the Borel plane. That's a universal property of resurgence proved by Ekal. But just a remark.
Yeah, thank you. That's actually pretty interesting, because as you said, the Gromov-Witten partition function in some sense is the more natural object. If you want to interpret things geometrically, yes, yeah.
So I mean, it commutes with summation. So the exponential of the summation of f tilde is the Borel Laplace sum of the exponential of f tilde. It works. That's right. And everything stays resurgent, and alien calculus can help you to keep track of the singularities in the Borel plane, although they become hugely ramified.
So actually, a question about nomenclature. To call a function resurgent, is it the same as saying that it is the result of Borel resummation of some series? Are they interchangeable names?
I can
Arpan or David, yeah, anybody can answer. Yeah.
Oh, okay. So yeah, I mean, I mean, correct me if I'm wrong, but yeah, I would say that you call it resurgent if they're Borel resummable, because it's not always guaranteed that you can do that.
Well, there is an extra property. So not only the function is the Borel Laplace summation in some direction, so which means that in the Borel plane there is at least one direction on which along which you can take Laplace. But moreover, the analytic continuation of that thing, which is defined near that ray, is nice. So there is the extra property of having endlessly continuable analytic continuation. So it simply means that singularities should occur, no natural boundary, only isolated singularities. In the Borel plane, you may have singularities of any kind, but they are locally isolated.
I see.
So which allows for calculus to compute these singularities in a tractable way.
I see. Okay. Thank you. So, Arpan, a question. So, you said at various points that the fact that the conifold case did not have wall crossing made life simpler somehow. So, but do you expect this kind of formalism to extend to cases that have wall crossing as well?
I mean, there's no reason to not expect it, but I think it'll be much harder to say anything about it. Okay, I mean, at least on the geometric side, I can comment on that because so these TBA equations that you have, like they are very non-trivial to solve. But in the case where there is no wall crossing, in the uncoupled case, basically the TBA equations becomes a prescription for defining like half of the Darboux coordinates in terms of the other half. Like you can always solve them in that case, and then you can actually the last result, at least, you know, it does make use of the uncoupled nature of the problem in a very explicit way. But the first part of the talk, we don't really know how far it extends, but at the moment we are setting our sights on saying something for the uncoupled case, because I think the fact that there was such a nice function to work with, the Brisson's triple sine function, I don't know to what extent that generalizes beyond the uncoupled case. I suppose a result very similar to this will hold, but it'll need a lot more work.
Thanks. Any other questions? I don't see any other hands raised. Okay, so let's go ahead and thank Arpan again for a wonderful talk.
Thanks,
and yeah, thank you all for joining.
Thanks again for the invitation and organizing the seminar.
Yeah, thank you. Thank you. So I'll go ahead and stop the recording, but if people want to hang around, that's okay.